So yes, it's my job in this summer school to give more details on the construction of these spaces and on their properties. And so if you want to understand this construction and why they are constructed this way, you need to know what you want to do with them. So you need motivation, and motivation has already appeared in several talks. I mean, the main motivation nowadays, arguably, is the so-called categorified local Langlands correspondence. And it already appeared in Xin-Wenju's talk and in Matt Emerton's talk yesterday. It will certainly appear in talks by Farg and Scholze and by Benzvi. So there are a bunch of papers associated with these talks, which I think appear more or less at the same time. So there is I don't claim there is any preference order, but so there is Farg-Scholze, there is Xin-Wenju, maybe Benzvi, Shen, Helm, and Nadler, and there is a paper by Helman. So there is a difference between these papers that these two ones are over ZL, and these two ones are over the complex numbers. So a common feature of all these papers is that what they predict is, so they predict sometimes much more than this, but what I will retain for this talk is the existence of certain fully faithful functor from rep, so say lambda. So lambda will be either ZL or a characteristic zero field of G of F. So my notations are here. I think these are already standard notation. And to something which basically is made from covariant sheaves on a space of parameter. And this is the space we want to construct. And I think it's given the diversity of the audience and different background. Some people have done only complex automorphic forms. I think it's interesting to start with the complex story. So let's look at the complex story. So in this case, you would think that there is not really any difficulty in producing varieties that parameterize Langlands parameters, because you don't have difficulties with continuity. But actually, there is still some subtlety, and the main difficulty you have is to know what kind of parameters you want to parameterize. So the first question is what parameters you want to classify. So if you look at Olivier Taïbi's first talk in this summer school, what is a parameter? There are several avatars, but in the classical Langlands correspondence, a parameter is usually some phi, which goes from WF to the L group, which has the following properties. So it should be a L homomorphism. And what you want is that phi restricted to WF is continuous. You want that phi, or I would say phi or phi, I don't know exactly which one I should choose, but you will understand. Phi restricted to SL2 should be algebraic. And then you also ask someone that phi of a Frobenius should be semi-simple. At least phi of any element in the W group.
There's no SL2 on the left side
Oh, sorry. Thank you. Yes, that's the point. That's the main ingredient in this case. Okay, so far so good. So as you know, there is another avatar for this kind of object, where instead of parameters morphism, instead of yes, homomorphism like this, you just look at so-called Veil-de-Lune representation. So it's a pair where now Rn, say, where R is now really from WF to G, and N is an element in the Lie algebra of G hat. And again, you have some condition that R should be continuous, and R of a Frobenius should be semi-simple. And and then you have this, so add R of W for any W in the Veil group of N should be, yes, something like this, Q to the new W. So you can guess from this formula what is new. Okay, and so you have two avatars, and so what's the relation between these two ones? So you have a clear map from 1 to 2. So if you have phi, what you do is you define some Rn in the following way. So you have to be careful. This is not naive restriction. This is some kind of diagonal restriction, where so R of W will be phi of yes, of W and say this matrix. Okay, and N will be the derivative at this matrix. Okay, so so you have a map in this direction, and so if you want to go the other way, so you have Jacobson-Morozov theorem, which tells you that this map is surjective, and it induces bijection on. Yes, so I forgot to say, but a Langlands parameter actually is a G hat conjugacy classes of this kind of object. And what's nice is that Jacobson-Morozov will tell you that it induces a bijection between conjugacy classes. Okay, so this means that after all, you could maybe take any definition and try to make a variety that parameterizes this kind of stuff, and it's quite easy to construct such a variety. Maybe it will be in variety because I'm not fixing a depth here, but if you fix a depth, it will be just a variety, so quite easy. So you get two varieties, and you may think that they look the same. Sorry?
Yes, the same as simplicity condition.
Yeah. That's the first remark. Okay, thank you. So the first remark I want to say that if you really want to have a nice algebraic varieties, you really should drop. So that's something which might bother people who are from classical Langlands background. You should really drop Frobenius semi-simplicity. So why is that so? And so you should drop it, and you should not be bothered. Should not be bothered because you will recover it when you take the coarse quotient. That means invariance. So the picture. So if you have never met such a phenomenon, the picture you have to, actually you already have met such a phenomenon. So the picture you need to have in mind is that if instead of this group you want to just look at morphism from Z, so just element from, say, from G hat, is that, okay, there is no, toy. So there is no nice algebraic variety structure on the state of semi-simple element. Okay. So it's certainly a constructible set, but it's not a locally closed subset of G hat. But so if you want to parameterize, say, just Frobenius, and so semi-simple classes of element, then you must not look at the set of semi-simple elements, but really at all the elements, so G hat. So you may be a little bit bothered, but when you go to the coarse quotient, you take the spectrum of the invariance of under conjugation, then you know that you have this isomorphism, from Chevalier-Steinberg, I think. Okay, which tells you that the algebra of the coarse quotient is just T hat mod W. T hat is the maximal torus. W is the Veil group, and so what this means is that the points of this space are really the semi-simple classes, and so that's exactly what's going on in this what will go on the space of parameters. So you should just drop Frobenius semi-simplicity. Okay, so this.
Laplace parameter without any equivalence relation.
Yes, yes. Before taking it, and then you take the quotient. Yes, that's what it means. So yeah, so that's a problem in the theory. There is no, I don't know if there is a word for when you say modular space. You mean the modular stack or the coarse quotient, but sometimes you're just happy with the thing that which is called sometimes frame moduli, which is the thing before quotienting. So maybe I will use the word frame moduli for this. So okay, so now, as I said, it's quite easy to see that this morphism or Veil-Delin representation are parameterized by a variety. So, but what I claim is that they are very different actually. So let's take an example. So let's look at X1 unramified. See the variety of, so this is an unramified part. So it classifies only Frobenius and the morphism for SL2 or Frobenius and the N for X2. Okay. And you have this map, which is clearly algebraic. And then you may wonder what it looks like. So let's have a look at the case G equals GL2. Then on the first line, so you have basically two possibilities for SL2, either it is trivial or not. So in this case, what you get is a component where phi is trivial, and another component where phi is non-trivial. And this component, they don't meet. Okay, so this is really a disjunction. And I mean, if you want to be explicit, so this one is just isomorphic. So it's 4-dimensional. It's just isomorphic to GL2, and this one is isomorphic to C star times PGL2. It's also 4-dimensional. Then let us look at the next one. So there, again, you have two components where n will be 0 and one where n will be non-zero. But as you may think, that this will not be closed, this will be open, so maybe you have to take the closure. And indeed, you have to take the closure, and this closure will meet this one and the intersection. So these are, again, 4-dimensional. So this is still GL2, and before taking closure, this is still C star times PGL2. But, so once you take the closure, I'm not sure I can really say what it is. But the intersection is the locus where you just classify a Frobenius, which has, so the two eigenvalues should have ratio Q. Okay, so, and it's 3-dimensional. So you think you see the geometry is really very different. So if you want to use, I mean, so if you want to know which one is good, you certainly need to know what you want to do with it. So before answering this question, maybe I just make an additional remark. So here, what you see is that actually this looks like an open subset of a normalization of this. And there is a paper of Bertoloni, Meli, Imai, and Lucis, where they look at the general case. And they prove that it's always, this morphism always separates the irreducible component. And it's birational in some sense. And they also prove something interesting, that for GL, starting from GL4, you have an example where this map is not surjective, actually. If you drop the Frobenius semi-simplicity, then it's not true that you can use Jacobson-Morozov to get. So this map is not even surjective in general. Okay? So let us look at what the coarse quotient look like. So, so now, what is x1 mod g hat? So, as I said, what you will do is just semi-simplify the Frobenius. So this really, so this set is really a priori the set of semi-simple parameters, which is nice. So that's the same phenomenon as for the Chevalier-Steinberg stuff. And here, what does it look like? So in this case, you will also semi-simplify Frobenius, but actually you will also collapse the n. Okay, so you will semi-simplify the n, so it will get to 0, so you will just forget about the n. And so this variety is what I think Vaughan called the variety of infinitesimal character, something like this. So this is Vaughan terminology. And the map is just the map which takes a parameter to its infinitesimal parameter, infinitesimal character. So, okay, so now you have, so if you want a categorical stuff, you have to decide which one is the right one. So what's your opinion? So this one looks like a very good one because it really parameterizes what you want. But now, let's look at what we want. So I don't know, it already disappeared, but so we want something which is fully faithful from from the covariant sheaves. So let's just look at what it should what it should do on the trivial representation and on the Steinberg representation. So the trivial representation, it's irreducible, it's indecomposable, so it should map to something indecomposable, which is, so if you want to use this, this x1, which has two connected components, it should map so only to one of them, and the same for the Steinberg. And then if you want compatibility with what you know about the Langlands correspondence, the trivial one should be in this component, and the Steinberg one should be in this one. And that's not possible, because then what happens with the induced representation? It's a non-trivial extension, but you cannot have a non-trivial extension between sheaves on different connected components. So you can discard x1 for sure. It's not the right one. So the question is x2 the right one? Yes, the answer is yes. And so x2, so the output of this is that x2 turns out to be the right one. At least it's the one that shows up in the work by Helman and Benzvi and co. So that's a 2 here. Okay, and so that's it for the complex story. So I won't say much more because now I want to go to the l-adic stuff. What should we maybe? So in the l-adic setting, what do we want? Again, we need to know what we want. And I think it's maybe easier to then come back to the original motivation. So actually these spaces in the l-adic setting, they appeared in literature before before categorification of local Langlands had emerged. And they appeared first in a paper by David Helm, which was about local Langlands in families. So this will be, so in the l-adic story. So these are I mean, in Mathemeton's talk, he talked about the old days. So these are the old days of the theory, just before, so pre-categorification. So this is motivation 2 somehow. So the advantage of this motivation is that you see better what you want for your spaces. So this is local Langlands in family. So LLIF for short. And here the names are basically Emerton and Helm. And that was for the group G and GLN. And then there is subsequent work of Helm and Helmos, which I will refer to later. So what was it about? So LLIF, it asks for a correspondence which to some Galois representation associate some morphism to the, so yeah, some representation of, so that's not very original, as usual. And so from rho to Gn lambda, I will tell you what is lambda. You want to associate a representation of the group GLNF. And here, an important thing is that lambda is complete local Noetherian. So ZL algebra, but actually I will need to have a lot of root of unity at some point, so maybe I will take WFL bar algebra. And okay, so that's the context they are in, and they want to associate some representations. Of course, you need to know what kind of properties you want for this correspondence. So there are a lot of requirements. I won't make the full list here. But among the requirements, one is, so there are, I think, two important ones. One is that it should interpolate in some quite loose way, but still interpolates the classical local Langlands correspondence at a generic point, say. So so it's very rough actually. So this is, yes, I forgot to say here I want it to be flat. So all generic points have characteristic 0, and then you really have classical local Langlands correspondence. But actually, what you want to interpolate is not exactly classical Langlands, but it is the modification due to Breuer-Schneider, and this is related to the second requirement, is that you want your representation to be co-Whittaker. And again, I won't tell you exactly what it means, but what is important is that co-Whittaker means that you should be a quotient of the following space, which I hope has already appeared in previous talk, which is the space of Whittaker function. So here, U is a maximal unipotent subgroup of GLN, and psi is a regular character of U of F, and so this is where you need lots of roots of unity, and that's why I'm sticking to this. But okay, you can descend the theory afterwards if you like. So should be.
There was a question on the chat on Zoom. So could you repeat the argument why x1 is not the right object to consider?
Why?
Why x1 was not the right object to consider?
So the idea is that the Steinberg is.
Can you repeat the question so that everyone?
Okay. So there was a question to repeat the argument why x1 is not the right one.
Yes.
So if you want a functor like this, fully faithful, and so you have the Steinberg representation. It's an indecomposable object. It should be mapped to something which is supported on only one of these guys. So by compatibility, it will be the one where SL2 is different from 1, and for the trivial representation, similarly, it will be supported on the other component. But then, if you look at this non-trivial extension of the one of trivial by Steinberg, then it should correspond to some non-trivial extension on the other side, but there are no non-trivial extension because support are disjoint. So, okay, so I don't know if this space has already appeared, but so this is the Whittaker space. Okay, so maybe a little bit of background. So why would I care for such a correspondence? So the idea, I think it was implicit in the end of Emerton's talk yesterday, is that you want a device that allows you to describe the completed cohomology of Shimura varieties, so say unitary Shimura varieties here. Maybe after localization, have some Eisenstein, non-Eisenstein modular representation. And so this would somehow, what you expect is that this completed cohomology would still, although it's not irreducible at all, it would still have some kind of factorization as an infinite tensor product, which is non-trivial. And then you would like some kind of purely local recipe to say what are the local components, and that would be the device that gives you this purely. So so it explains why you want this, and then this co-Whittaker. So my understanding of this co-Whittaker. So there are several reasons, but one reason is that I mean there is a geometric reason for GL2 that there is something called Yara's lemma, which imposes that what's going to happen in the cohomology or the homology has to be co-Whittaker. So and that's somehow conjecture to all in higher dimension.
So can you repeat again how this lemma is called?
Sorry?
What is this lemma called?
Ihara's lemma?
Yeah.
I-H-A-R-A. Sorry for my... Sorry?
So what exactly should be a quotient of this W? The image of this?
The pi of rho you're looking at. It should be some quotient of this, such that when you take U psi invariant, it is an isomorphism. So So basically, the main condition is that you want that the u psi co-invariants are isomorphic to lambda, and that there is no quotient which is not co-generic of in some sense. Okay, so but.
What's your definition of a Ihari lemma? Because I know a kind of Ihari lemma, but it is
yeah. So Ihara's lemma is well. So maybe we can discuss this afterwards. But it's just that it tells you that the trivial representation. So the only non-generic for GL2 is trivial representation. So just tells you that the trivial representation won't appear in the as a sub. So that's.
Sorry, you mean like the Whittaker character size depends on this rho, or is that what you mean?
Psi depends on?
I mean, the psi is defined by this rho, or this psi is some chosen.
Psi, I will fix it and choose in one but if you change psi, you get an isomorphic representation, so you don't really. Yeah, so you don't.
The representation pi you want depends on rho. So you mean all the pi rho appears as a quotient?
Yes, right.
As a psi.
Yeah. Yes, any pi rho that you want to construct this way should appear as a quotient of this way. I mean, this is a huge stuff. It sees all components. It's not finitely generated. This is a huge guy. Yeah, so maybe just a remark is that maybe to follow then Helm's strategy is that it's an important remark. So yes, if you want to understand quotient of this guy, you want to understand endomorphism maybe, and so the endomorphism of this guy that receives so n of W. So say so let me do this over any ring sufficiently big. So n of W should receive the center. Of course, the center of the category. So that's tautological. But what's happening in this case is that okay. So that's something general that you can define for any reductive group. But what is nice is that in the case of GLN, this is an isomorphism. I mean, it's not a remark. This is really, I mean, it's not non-trivial. So maybe remark is not the right word, but the remark is that this is not true for other groups, and that will certainly create a lot of difficulties. Okay, so now what are Helm insights? So you see, you are really, as Matt Emerton said yesterday, you are really here, in the old days, you were really in the world of deformation theory. So here, just you're looking at complete local Noetherian algebra, which means really you are looking at deformation. So if you want to cook up a correspondence, then you have to, maybe the best way is to look at what's happening on the universal deformation. So universal stuff will tell you, if you can do the universal stuff, you can do everything else then. So Helm's insights is that this conjecture, so LLIF should follow from, so it should rather involve isomorphism between the following stuff, universal deformation ring of say FL bar gamma representation and completion of the Bernstein center or of the ring of endomorphism at some closed point. So maybe, yes, so this will be, say, CL. So basically, there should be some kind of bijection between the representation here, mod L representation of gamma f and the close point of this space. And moreover, the universal deformation ring should correspond to the completion. So when you see this, you see that you are in better shape on the right-hand side, because here you have already the algebraic interpolation of all these completions. So here you have really a bunch of completion on each side, but here you have, I mean, these completions come from something which is algebraic, so that's much better. So Helm's insight was to say, okay, but there should be something algebraic also that interpolates all these universal deformation rings. And what can interpolate all the universal deformation rings? A moduli space. Okay, so Helm, that should be interpolated. And that's the original, I mean, that's, I think, the first motivation for which appear, I mean, historically. So nowadays, I would say really the main motivation is categorified local Langlands, but historically, it was maybe an explanation why these spaces showed up. So it should be interpolated by some moduli space.
What do you mean by interpolate?
Sorry?
What do you mean by interpolate?
What do I mean by interpolate? So if I have a moduli space, so in general, that's a general fact that if I look at the formal deformation, I mean at the formal neighborhood of some point, it will correspond to deformation of this of the thing I'm classifying at this point. So that's what I mean. I would just want a moduli space and algebraics so that the spatial fiber. So actually, I will write it right now. So the spatial fiber should parameterize these guys, and then the completion should be these guys. So maybe, yes, that's what I should write now. So what are the desiderata? Okay, so you want a moduli space such that, so on the spatial fiber, you really want what I've just said. The set of FL bar points of this space should be exactly the set of representation, mod L. And then if you take a set, you want that the completion at such a point, formal, should match the deformation ring, universal deformation ring. And then there is this interpolate classical local Langlands correspondence condition. And what it means here is that, so you have three conditions, is that what happens with the QL bar point? Well, they should be related. They should be basically Langlands, local Langlands parameter. So that should be, at least there should be a map from this to the local Langlands parameter. Because, yes. Because you want to formulate an interpolation condition, I mean a condition on say characteristic 0 points, you need of course to relate your points to Langlands parameters. Okay, so that's the bill you have to fit. So let's try to do this. So maybe I just okay. So before I explain how you do this, maybe let me explain how you once you have such a space, how you finally construct the representation row. So such a space was first constructed by Helm. And then that was for GLN, and then recently many people have generalized the construction for any other groups, and that's what I'm going to tell you afterwards. And once you have this this space, so Helm's reformulation is the following. is that there should exist an isomorphism. So yes, so this space, I will give it a name. Say for now it will be X. It will be the spectrum of some ring R, and on this X there is so it's over ZL, okay, and on this this space, so this is a ZL scheme. And on this space, you have an action of GLN, which is G hat, if you like. In general, it will be G hat. Okay, and then you can look at the invariant. So that's the ring of function on the coarse quotient. Okay, that's the ring of function on the coarse quotient. So GLN. Then you map to that there should exist a map, an isomorphism to the center of the category. And then you can compose with the endomorphism of the Gelfand-Guariev, so the Whittaker space. Okay. So there should exist. So that's the reformulation by Helm. So actually, this reformulation can make sense for any other group. It's more difficult to make sense of this right now. I mean, to have an analog of these local Langlands in families. But this statement, you can make a similar conjecture in general. So except that you don't expect in any way that there should be an isomorphism here, neither here, but the composer, that there should be a map. And then the compose map should be an isomorphism. And such a map was actually already constructed by Fargenschulze. So maybe I'll come back to this later or next time. Okay, and then so it was proven finally by Helm and Moss. And so you may wonder, how can I get from this statement to this one? Because it may be not clear at all. So this is what you do. So the recipe is the following one. So I will be using it afterwards. So you start from rho, which is a representation to some GLN lambda for some local Nesserian complete algebra. And it corresponds to some morphism by universality from R to lambda, okay? Because this is a modular space. And then inside of this, you have R fixed by GLN, not F, fixed by GLN. So you get a map here, and what you can do is just you take the Whittaker family, the Whittaker representation, and then you base change it to so now you know by this statement, you know that it is naturally a module over RGLN. So you can base change it to lambda like this, and now what you get is really a representation of. I mean, it's clearly a quotient of well. I mean, it should be co-Whittaker, but it's not the right one because you are still lacking the first condition that you should interpolate the classical local Langlands. So what you do, okay, is you have to look at what's happening at generic points. So you go to the product of eta generic point. And okay, so you map into this guy, And then here, you know, so you have some kind of universal co-Whittaker stuff, and you know by local Langlands correspondence or by Breuil-Schneider correspondence, you know what should be matched to a row specialized at lambda, at eta. And so you just take the map to the product over eta of, so this is, so I don't know, LLC, Breuil-Schneider of row specialized at eta. Okay, so this is some kind of co-Whittaker version of the usual local Langlands correspondence. Yes, and then, so you have this map, and then you define pi of rho to be the image. And that's what you want.
In the second last.
Here?
Yes. What is that? It looks like L.
Here?
Yeah.
This is R. This is the same as this one. Or if you like, yeah, yeah. I mean.
Sorry. What is the thing to the right of the W?
K of the. This is the residual field of the residue field of the generic point. Yeah, so it looks like a funny recipe, but it is really, I mean, Emerton's theorem is really that for GL2, this is really what's happening. This is really showing up in the completed cohomology of modular curves. Okay, so what do we want to say next? Maybe something like the connection to, what is the connection to category? Categorify. What is the connection to CLLC? That's the categorified version of local Langlands correspondence. So, yes, maybe I should change. So the connection. So there is one thing I haven't recalled about this categorified local Langlands correspondence is that not only you want, say, so here it would be over ZL or over the Witt vectors or FL bar, no matter. So not only you want a fully faithful embedding in co of X mod GLN, so it will be in general G hat, say, but here this is mod GLN. But you want also another property, which is some kind of normalization, is that this map should take the Whittaker space to the structure sheaf. So this was already explained, or actually it appeared in Shin-Wen-Zhu's talk. So that's one of the requirements, and then you see from this that, of course, this will imply local Langlands in families because it has to be fully faithful. So it has to map to be an isomorphism between the endomorphism ring of W and the endomorphism ring of the structure sheaf. But this is nothing that exactly the ring we want. Okay, so categorical local Langlands certainly implies local Langlands in family, and if you think in terms of yeah, so they both use the same modular space somehow. I mean, not the modular space, but framed modular space. But local Langlands in families only sees the coarse quotient, I mean the ring of invariants, while categorified local Langlands correspondence certainly needs the stacky quotient. And yes, so so you may think that there is really some huge discrepancy between both, but actually for GLN it's not so. Yes, yeah. Of course there is a huge discrepancy, but so for GLN again, there is still a recipe. I won't claim that LLIF implies CTLC, but at least LLIF gives you a functor, and then you can hope this is the desired functor here. So LLIF provides a functor which basically maps a representation V to some V tensor Z L bar GLN F rho univ pi of rho univ. So what is pi of rho univ? So rho univ is the universal. It's a universal object on. Maybe you have to know that rho univ is really a representation, but let's admit this. So rho univ, there is a universal object, and it turns out to be a representation. So you can play the same game as just above, and define. Yes, it was. Yeah, you can define pi of rho univ to be the image of some similar map, and this guy has an action of GLN because it's a base change from R fixed by GLN to R. Okay, so there is an action of GLN on the right-hand side, and then you take the image, so you take a quotient, and you can check that the ideal is actually stable under GLN. So there is an action of GLN. So what you get here is really something you can consider as a. So this is a GLN equivalent R module, and this is nothing but a sheaf on the stack. So it gives you a functor, and actually, this guy somehow arose in Merton's talk. It was called L infinity, except that in Merton's talk it was for L equals P, but this is the version L different from P of L infinity, and it's so okay, so it provides you a functor, and I think at least Helman has an explicit conjecture that this is the right functor, maybe not over ZL, but at least over C. And I think Shimunzu also mentioned it. And okay, so you expect that this functor is the right one, but of course this is really a recipe that only works for GLN for many reasons. And one reason is that for any other groups, the Whittaker space won't see many supercuspidal, for example. So
is the tensor product derived? Or?
Yeah. Sorry, thank you.
Jean-François, could I ask, in the top board, you have this recipe for pi rho, right? Is it possible to give an example, say for GL2, if you take an parameter of trivial representation?
Yes, it's certainly possible to okay, maybe.
What's this product? Like how many generic points are there? Right.
So it depends on the lambda you're taking, right? So you have to take a family of, for example, something where Moduli degenerates, and look at what it should be, and yeah, something we can do. Maybe I have to sit down to, but yes, you can really be very explicit.
For GL2, is the product either over one element or two elements? That's it.
No, but I mean lambda is anything here. So lambda could have as many generic points as you want. But if you take the universal family, and yes, and in a ramified case, yes, maybe, or in a complex case, yes, you will have just two. As we saw, there were two components, so there are two generic points, and you have to make some modification at both. One of them should be trivial, and the other one should be non-trivial somehow.
Okay.
Yes.
Also, I have a question. In this map, what is the difference between second and the third objects?
Second and third. So yes. So this modified version of local Langlands correspondence by Brian Schneider on the right-hand side, it's only a quotient of the W tensor K eta. But you know this quotient. So you don't know what's going on outside characteristic 0 at this point. But you know this quotient. So you take this quotient, and then you take the image, and this is what you want for your family. Okay, so now let us finally come to the construction of the space we are interested in. So so this was just somehow motivation, and there is a list of desiderata here, and we have to fit this bill. And so we want a space that has these three properties. And so actually we ended up the complex story with some spaces of Veldolin representation. So Veldolin representation make perfect sense over any field, so you could just take Veldolin representation. So you could take the space, the modular space of Veldolin representation. It would give you some object, and then it would have to fit this bill. And yeah, so if you look at FL bar points, then you get a Veldolin representation instead. And what do you do with n? I mean, sometimes you can maybe exponentiate it. So if L is big enough, maybe you can really use this space of Veldolin representation, because you can do the exponentiation trick as usual. But in general, it will say that it will not be a good space. It won't be reduced nor flat, nor I mean, lot of problems. And then and more prominently, you see that the FL bar points will not be what you want, because there is this n you you don't see what you can do with it. So you need something else, and then you need to remember what you need. You need to remember a third avatar of Langlands parameters when you are in the l-adic setting or in the q-l-adic setting, so not complex setting, but so the third avatar is 3. So these are the continuous morphism for the l-adic topology. So phi from WF to, say, LG of QL bar, which are l-adically continuous and not continuous for the discrete topology here. And so so there is a Grothendieck theorem which tells you that 2-mode conjugacy is in bijection with 3-mode conjugacy. So this is another avatar that we can use, and this is maybe this fits better in all this picture also. So so now what we want is quite clear. We would like to define a modular space, so it should represent a functor. So we like to represent a functor, which to any ZL algebra, which to any R associate, well, the space of continuous, say l-adically continuous morphism from WF to LG of R. So you can think of GLN again. It won't make much difference. Yeah, so the problem, of course, is that you're not dealing with a topological algebra here. You're not just dealing with an abstract algebra, so you don't know what it is. And so there are several approaches to this problem. So that's the main problem you have in the l-adic setup. Xin-Wen Zhu already told us about one approach. So if you remember, what he defines is an in scheme. And in general, so the merits of his construction is that it works in high generality, except that, yeah, maybe what you get is not an algebraic stuff, but there are a lot of formal direction. Sometimes it could be just purely formal. And okay, so here we really want something algebraic. So if you start with Xin-Wen Zhu's approach, then you have still to work to prove that it is algebraic and there is no formal direction. So you have something to do. So yes, so I know. I think I know 3 approaches. So Xin-Wen Zhu. Which was, it didn't seek to define a scheme, but really an in-scheme. Then there is Helm, original approach, which is quite maybe pragmatic here, except that you maybe don't see how it will generalize in general. I mean, for other groups, say, other than the Galois group of local field. So Helm's approach is the following. So, well, pragmatically, you want to define what it means to be l-adically continuous, but there is one case where you can really say what you want is when R is l-adically separated. So one, if R is l-adically separated, then you declare phi is l-adically continuous if, yes, for any M, the composed map modulo M is continuous for the discrete topology here. Okay, so that gives you a definition, but only for l-adically separated. And then, second, if it is not l-adically separated, so in general, there should in general it is phi is l-adically if R is l-adically. Sorry. So in general, you would say that phi is l-adically continuous if there exists R0 l-adically separated, phi 0 like this, really l-adically continuous, because now you know what it is, because it's R0 is l-adically separated, and you want that your phi comes from R0 by push forward. So that's a very weird definition, right? So if you look at the bill here, it's not even clear that you really get the correct QL bar points, but you can prove it, that you really get the QL. What is even less clear is that you get something representable, because it's not even clear that it is sheafy, for example, that is a sheaf because of, this condition is. However, in the end, it will be a consequence of the construction that finally it works. But a priori, doesn't look promising. Then the second and the third approach is the one by Farg and Scholze, and it uses condensed mathematics. So somehow it's it uses condensed mathematics. So the context will be quite different. You will be parametrizing. So the modular space should be. So instead of defining what it means, we're defining what it means to be l-adically continuous. They just parameterize something else, and what they parameterize are map. Say R, so I will write it in that way. So map, so this should be a condensed ZL algebra, and what you want to parameterize are maps which are condensed maps of condensed group. Okay, so. But actually, you can just recast all this in terms of topological terms, and what it's so okay in topological terms, what this means. So yeah, so it's quite important that they use their condensed the condensed formalism, because it is somehow imposed by. I mean, this is what comes up naturally from their l-adic formalism for l-adic sheaves on Bungie. So, but if you want to somehow have a more classical language grasp on these objects, so in topological terms, what you do is you endo R with what Qin Zhu call the end l-adically topology, adical, so and l-adic topology. And what is it? It's a finest topology which induces the natural topology on all finite ZL submodules. And then finally what you are, and then instead of this l-adic, finally what you are parametrizing are really, so then you have to make sense of what it means to be is continuous. So you can take, for example, a faithful representation of your L group into some GLN, and then you can, once you have a topology on R, then you can make sense of what it means for a representation to be continuous. Okay, so this is continuous in that sense. So this is a third approach, and again, one difficulty is to show that it is representable. So we have three approaches. The first one is representable somehow for free, but you need to show that it's algebraic. The second one, it doesn't look it will be representable, but in the end it will be. And the third one, you have to prove it is representable. And what's funny is that in the end you get three different. What's funny is that in order to solve all these problems, you use the same trick for all three problems. And in the end, what you get are the same objects. Wow. Okay, I'm nowhere close to.
Can you repeat again on the, like, this is the Galois side. What is the representation side? Which representations you are considering? Can you repeat again?
Yes. So what I just mean that what you want to parameterize in this case are continuous morphism like this. Yes. With so what you have to say what it means continuous, then maybe you go to some GLN R with some faithful representation, and then you know what it means to be continuous. I mean, so what you want is that W, any vector on your representation should have an open subgroup, should have, okay, should belong to some finite ZL module, which is stabilized by some open subgroup, and such that the action is really continuous for the ZL topology.
Yeah, so there is a, like...
Yeah, so there is a really concrete, but it doesn't tell you it's representable, right? Okay, so what's interesting is that, so in the end it will turn up to be representable, but if you replace WF by IF, for example, I'm not sure that you can, I don't know what's happening, because the crucial point here that makes all these approaches work and finally coincide is that you have Frobenius. So that's what we are going to explain, maybe. Yeah. And somehow this is something which also appeared in Sam Raskin's talk. So when he told us about this log-sys restricted and log-sys arithmetic, so the log-sys restricted was at lot of formal direction, and log-sys restricted was much better behaved, was really a scheme. And that would come from Frobenius. Okay, so. Okay, so so the magical feature, or magical. So okay, so let's be pragmatic. So where the problem can come from? We are looking at l-adic continuity, and we are this group WF, and the only problems can come from the l-adic, so from the pro-L subgroup contained in WF. And actually, they are very simple. They are procyclic. So so it should not be difficult. You are just in WF, you have PF, which is pro-P, so there is no problem with PF. And then you have the quotient IF mod PF, which maps to the L, and this is where the problem comes from. So let's look at this TM quotient. And so inside there will be IF, which is procyclic. And this is the guy which is responsible for the difficulty to get some continuity. And so let's try to get rid of the difficulty just by discretizing this guy. So choose a generator. And then choose also Frobenius. And then we look at the following subgroup. It's generated by these two generators, and so this is some group which appeared after 5 minutes in Shin-Wenzu's talk. So I'm there only after 1 hour and 10 minutes. But so this group is just so the Frobenius acts by multiplication by Q on this guy. So this is a discrete group. And it sits in our tame group. And maybe I will also define WF0 to be the inverse image of WT0 in WF. And okay. So that's a dense subgroup of WF, and then the topology I want to endo WF0 with is most natural one. So topology will be a natural, the natural one on PF, and the discrete one on the quotient. Okay, then once we have done this, we have got so somehow we got rid of any pro-L stuff in our group. So we can now really look at a very simple object, which is the following. So from R, so from ZL algebra to sets, which to an algebra just associate. So maybe I will change a little bit my notation. Now I would like to call it Z1 for cocycles, but you can just think in terms of endomorphism if you like. From this guy to G hat. So this is just the set of endomorphism from WF0 to LG, if you prefer. Sorry, so evaluate at R. Yeah. Yes, and this is clearly representable. So, okay, this is clearly representable. Maybe not so clearly because I did not fix. But what I can do is I can say fix.
You need to say continue with respect to the discrete topology on G of R.
Sorry?
Do you need to say continuous with respect to the discrete topology?
Yes, yes, that's what I mean. Yes.
Can you repeat that so everyone can hear it?
So continuous. Yeah, so the question was what continuity condition, so continuous for discrete topology on LG of R. And okay, so in order to have a very nice scheme, let's fix some open subgroup of PF and just look at, let's assume it acts trivially on G hat, and let's look at this space. So now it's really finitely generated. The L scheme. It's represented by some closed subset of, so this is a finitely generated group, so just take generators, W1, Wn, then this is a closed subscheme of G hat to the n. And, okay, and so does it fit the bill? So this gives you a space, and what I claim is that it fits the bill, which is here. So what was the bill? The deal is that the FL bar points should be Galois representation. Okay, but look at the FL bar point. So maybe think of GLN in all this story. Okay, think of GLN. So you're going to have, so the FL bar points are representation from WF0 to GLN of FL bar. There's certainly factors to some finite quotient. Okay, and then they will give you representation of really a Galois group. And the same applies for the completion, because at each level of your completion, it factors over the Galois group. So when you go to the limit, it factors to the Galois group. So maybe the only non-clear point is why the QL bar points are good. Okay, so what you need to understand is why the QL bar points are the right ones. So the claim, and this is where we see Frobenius, the role of Frobenius. So the claim is that any phi, so maybe I will just state it for, yeah, I mean, I state it for any group and then prove it for GLN. Any phi from LG, so from WF0 to LG QL bar extends uniquely to l-adically continuous. So I don't know, L phi from WF to LG of QL bar. And okay, and so let's prove it for GLN, say. So the first thing you can do is to use, so it's a bit of cheating, but when you can use a theorem of Iwasawa, which tells you that actually WF, and the same applies to WF0, is isomorphic, non-canonically, of course, but to a direct product, like this. Non-canonical, of course. Yeah, so, by the way, there is one issue with this construction, is that these choices I made are really highly non-canonical. I mean, basically, if you change the choices there, you really might end up with non-isomorphic groups. So that's a point of concern, but it will disappear very soon. But so this space might depend on our choices. It will turn out that over ZL it doesn't depend, because the theorem that next time. Okay, so just let me finish with this argument. So using this decomposition, you can just consider the case where P is the full wild group. Okay, and then you just have S and T, and then you look at phi S. You decompose it at its unipotent part times its semi-simple part. And the main point is that this guy, it is conjugate to its q's power. So I never introduced q's, but q is the cardinality of the residue field, q's power. So it means that it has finite order. So its eigenvalues will be roots of some q to the n minus 1. So it has finite order. And this one is unipotent, so it's exponential of something, because we are in characteristic 0. And so, well, you can just give a formula for the extension. It will be, say, exponential of, so this will be, now you want to extend this to WT, meaning that you want to be you want to be able to extend it to Z hat, or Z hat may be outside P. Okay. Yes. So let's say phi to the SA is just exponential of TL, the AN times phi S to the A. And this formula makes sense. This makes sense for any A in Z at say for A in ZL, if you like. Okay, so you had something only on discrete Z inside ZL, but actually you can provide a formula which tells you that you have such an extension. And so finally, this space really fits the bill. Okay, so I'm sorry, I'm out of time. So the next talk will be about the main theorems, main properties of these spaces and their coarse quotient, and maybe application to representation theory.
Thank you. Any short questions for Jean-François?
Sorry. What is your S here? Like, are you?
Yeah, so my notation really suck. My S is really the generator I have fixed.
Oh.
Yeah, so I think it was tau and sigma in Chimwell's. Tau and sigma may be a much better notation. So.
Other question? No?
Is the claim not true or with different coefficients?
So if you were, so yeah, so that's an interesting. So the question is if the claim true with different coefficients. So what is interesting with this space is that now you can define it actually over Z if you like. So say over Z bracket 1 over P not to have any problem with wild inertia. So you get a space over Z bracket 1 over P which somehow interpolates all L, which is very nice. One issue is that this space might really depend on your choices, but we will see that the quotients, the coarse quotient doesn't depend, which is nice too. So you have something about, so you have some space over Z bracket 1 over P, but it will not be true that you can, I mean, you cannot use exponentiation and use this, this formula. You really need ZL to be in the coefficient to have such a formula.
But it's true for any ZL algebra, the claim, right?
Sorry?
The claim is true for any ZL algebra.
Yes, so yes, right. That's what I was supposed to to explain just before, just afterwards, but that will be for next time.
Okay, no other questions, so we can thank again Jean-François.